Okay, our next model we're going to look at is Niels Bohr's model. And Bohr ended up being a lab assistant for Rutherford, so he knew quite a bit of Rutherford's theories, and he also previously worked for Thomson. So he basically took their ideas and fine-tuned it and came up with somewhat of a better model. So we remember we had an issue of Rutherford's model. If it was going to lose energy, the electrons would collapse. So he knew that there was problems to the model, but he couldn't trash it. He knew that there was some pretty specific things to it that were really good. So what he did was he basically said, well, the electrons aren't at just some random location. If we have our nucleus of the atom and we have electrons in orbit, they're actually in a certain specific level, and he said that those are based on how much energy that's required to get them there. And if they change a level, it's going to give off energy or absorb energy depending on if it jumps from one orbit to the other. So that's kind of where Niels Bohr's model came from. And the reason he figured out that these energies had to be at specific levels depending on what orbit they were in, he figured this out using spectroscopy, which is basically looking at a spectrum of white light. And so we know we have our Roy G. Biv spectrum. So what he basically did was he would look at different types of gases going through a diffraction grating and seeing what kind of spectrum was produced. So basically what happens in this case is he hooked up a gas to voltage, so he took mercury, hydrogen, helium, whatever the case may be, he would heat it up, and that would cause the electrons to gain energy, which then he thought they would jump from one level to the next. So if we had an electron at the first level and it jumped to the second level, he said when it makes that jump, it's going to give off energy. If it's gaining energy, it's going to emit some sort of energy, and we'll see that energy as a certain frequency. So when he shined, in this case we got hydrogen. If we shine hydrogen through a diffraction grating, he actually saw that we got a violet band of light, a bluish green one, and a red. So it actually gave off 3 different stripes of light at different frequencies. So he then deduced that, well, it's because these electrons are jumping. So if it jumped from to one level, that gave off a certain color. If it jumped to a second level, it would give off another color. Or if it made one jump from first to third in one motion, then it gave off the third pattern. So he sort of thought that for hydrogen, then we're getting these 3 possible jumps. So it's going from 1 to 2, 2 to 3, or 1 to 3 directly. And that's why we're seeing 3 different energy lines. Okay, so then what he did was he thought, well, what would happen if we do it in reverse? So in this case, he shines cold light through a cool gas of hydrogen, and all of the white light goes through. When it goes through the diffraction grating, it gave a full spectrum. But because in this case the electrons are absorbing energy, so if they're absorbing energy, then what happens is it absorbs those frequencies out of the spectrum. So you can see in this case the violet, blue, and red still show up, but they are taken away out of the spectrum. So in the emission spectrum, they emit those colors and nothing else. In the absorption spectrum, we see the full rainbow, and they absorb those exact same frequencies. So they kind of work the same as just one direction. The electron is going outwards, right? If it's speeding up, that means it's gaining energy, and if it's slowing down, it's going to go inwards, and it'll give off the same energy that we just calculated. So those same 3 lines would be whether the electron is going in or out. So the question is, which one's which? Is this bottom one the absorption or the emission, and is the top one the absorption or the emission? So basically they did some more experiments, and Balmer actually was a Swiss high school teacher, and what he found out was that for hydrogen he could actually figure out what those wavelengths are going to be. So he came up with this formula, this 1 over wavelength formula, and basically the idea is the n stands for the number of the orbits. So if we have our electrons at the first energy level and they jump to a second or jump to a third, that's our n 1, 2, 3. So he said the wavelength then is just 1 over 3 squared. If the electron is going from 1 to 3, he said it's going 1 over 3 squared minus 1 over 1 squared times whatever the constant is. You don't need to know this formula for the diploma, but the concept is important to understand, that as the electron jumps levels, it's going to emit a wavelength. So at the bottom here, what Bohr theorized then is as the electrons fall downwards, so let's go back to the previous page, so our bottom diagram, as the electron goes downwards, that means it's going to lose energy, so that's where we see the emission lines. So this diagram is actually for the emission lines. And then what Bohr said is as the electron speeds up, it's going to need more energy, so it's going to take it from the white light, so that one would be the absorption spectrum. The good news is you really don't need to remember which is which, you just have to know which level it's jumping from in order to figure it out. So in this case, we could use this formula, and it just says what would it be if it jumps from the base level to the third. So we go from 1 to 3, plug it into the formula, and we're good. We're not going to do many of these calculations because I'm going to show you in a few minutes the type of question you're expected to do, because this only works for hydrogen, and we need to know some numbers and stuff that's no longer in the curriculum. So other guys besides these guys, they actually figured out different patterns. So Lyman found for a hydrogen that you could go from 5 down to 1, 4 to 1, 3 to 1, 2 to 1, and that basically emitted ultraviolet light. If it left from level 5 down, it gave off ultraviolet light, so they named it after him. Balmer found out that if we only go from 5 down to 2 or less, it gave off visible light, so that's why we see the 3 colors that we do. And Passion was one that found out if we only go from 5 down to 3, it's very little energy, so that ends up being infrared, so we don't see those. So in this case, if we were to actually look at Balmer's series, we would only see 3 different colors. The rest of them would be outside of our visible range. So the key then is they did some more calculations, and they could actually figure out what the radius of the orbits are and what the energies of the orbits are. But once again, this only applies to hydrogen, so we're not going to use these formulas. And like I said, we just have to basically remember that as an electron jumps orbits, so if it goes from 1 to 2, it's going to give off, or it would absorb energies, but you'd see whatever that wavelength is going to be for that transition. And if we went downwards, it'd be the same wavelength, just one's positive, one's negative. One's gaining energy, one's giving off energy. Okay, that's the key thing you want to remember with that. So because these formulas only work for hydrogen, we're not going to basically use them. What we are going to do is you're going to get questions where they'll give you the energy levels kind of like this diagram. So in this case, it's saying we can jump from 1 to 4, and they give us all the energies for that transition. Okay, so in this first one it says, determine the total number of possibilities as the electrons fall from 4 to 1. So we could go from 4 to 3, we could go 3 to 2, 2 to 1, that would be 3 transitions, or we could go 4 to 2, and then 2 to 1, so that would be the same. Or we could go 4 to 3, which we already have, and then we could go 3 to 1, so we won't bother redoing these ones. So that would be another option. Or we could go from 4 to 1 directly. So we actually end up getting 6 different energy possible transitions to go from 4 down to 1. So that means if these were all visible, we would see 6 different bands of light for this situation. So part B now says, what's the wavelength if we go from 3 to 1? So if we go from 3 to 1, we can see we have negative 1.5 down to negative 13.6. All we have to do is subtract those. And you don't need to worry about the negatives. The negatives just mean one's absorbing energy, one's giving off energy, so that doesn't really matter. Just subtract the 2. So in this case, we would get 12.1. So that means we have 12.1 electron volts of energy being emitted. So now to calculate the wavelength, we just want to go E equals hc over lambda. So if we just go hc divided by E, that should work. So for h, we want to use our electron volts formula, so 4.14 to the negative 15 times it by 3 to the 8th for our speed of light, and divided by this 12.1. And if we do that calculation, we get an answer of 1.02 to the negative 7 meters, which would be about 100 nanometers, 102 nanometers, which would be beyond violet. If violet's 350, so in this case we would say it's likely ultraviolet radiation that would go from 3 to 1. And lastly, here's a diploma type question, so it looks exactly the same, just the number's a little bit different. So in this case, they're showing you 0 electron volts as being the base level, and as we go to different levels, it's going to gain more and more. So it'd be sort of like 1, 2, 3, 4, kind of like that. So this question says if the electron is in the 1.6.
Please contact the office.
So it's saying if it has 1.6 electron volts, we want to know how much it's going to take to ionize it. So ionizing it would be, it's going to go right out of the atom, so we're going to lose it completely. So we'd have to get to that 10.4. So 10.4 minus 1.6, if we do that calculation, we get 8.8 electron volts. So now we just need to figure out the frequency, so energy equals HF. So our frequency would be energy divided by H. So we take that 8.8 and divide it by 4.14 to the negative 15. And that gives us 2.1 to the positive 15 hertz. So that should be our answer, letter B. So what they're doing now in diplomas quite often, they'll tell you where the ionized level is, but ionizing just basically means we're removing the electron altogether. So the 0 would be the base level, so in this case our electron would be in the first orbit, we want to get rid of it completely, so that means it's got to get past that negative 10.4 level. And that's all.